Let me start by defining what a mass is. So this is a very general definition for any finite set of objects with finite automorphism groups. Its mass is what you get when you count its elements weighted by their automorphism groups. And then a mass formula computes an expression for such a mass. So the mass can be more accessible than the cardinality. And on the other hand, there's a philosophy that says that you should be counting weighted by automorphism groups to avoid double counting, so to speak. So that's a general mass. And then what are we going to be looking at? So here's a bit of a setup. K is an algebraically closed field of characteristic P, and A over K will be a three-dimensional abelian variety, so a threefold. Then such an A is supersingular if it's isogenous to a product of supersingular elliptic curves, and it's super special if it's isomorphic to such a product. And then S31 is the moduli space of principally polarized supersingular threefolds. So this is the Siegel locus in the moduli space of all principally polarized abelian threefolds. And now what is our set S? That's going to be the set lambda x here. So for any x in S31, we let lambda x be the set of all supersingular threefolds whose p divisible groups is isomorphic to the one that we started with. Note that for L not equal to p, all the L divisible groups are ZL to the 2g, so they're already isomorphic. And you can think of this lambda x as being some generalization of the superspecial locus. Now we know that this is finite, this is a result due to U. And so our goal will be to compute a mass of this lambda x for any x in S31. Okay, so let's start by looking a bit more closely at this S31. We'll study it through what are called polarized flag type quotients, or PFTQs. This was developed by Lee and Oort. And how it works is like this. We start with E over Fp squared, a supersingular elliptic curve, whose Frobenius endomorphism is minus p. And we let mu be any principal polarization of E cubed. Then an SPTQ for mu is a chain of isogenies like this, that starts with y2 lambda 2, which is super special. So it's this E cubed p mu. It maps into y1 lambda 1 and then to y0 lambda 0. And this chain satisfies some technical conditions that I wrote down just below. And P mu will be the moduli space of these FPTQs. Now, you can show that this is a two-dimensional geometrically irreducible scheme over Fp squared. And by these technical assumptions, we see that y0 lambda 0 is in fact principally polarized. So it's in S31. So there's a projection map that goes from this space P mu to S31 by sending this whole FPTQ to its last entry. This map is surjective and generically finite, and you can say that this P mu sort of approximates a geometrically irreducible component of S31. Okay, so then we sort of translated our problem into understanding this P mu a bit better. So how do we describe P mu? Well, we start by looking at the Fermat curve C of degree p+1 in P2. This is a very nice curve that we know a lot about. We understand its rational points over Fp and all extensions of that, for example. And it turns out that we can view P of mu as a P1 bundle over C. And that's because you can view C as the classifying space of isogenies y2 to y1, whose kernel is alpha p squared. And there's a section of this map that we call S that goes from C into T, say. And then what we learned from that is that for each x lambda, each supersingular threefold, there exists a mu, a polarization of E cubed, and a flag type quotient y, such that that is projected to our variety that we started with. And this y itself is then uniquely characterized by a pair t, u, where t is a point on the Fermat curve, C, and u is a point on P1. So the mass formula that we'll be finding will depend on the value of this t and u in the end. Okay, but let's add a little bit more structure to this space of flag type quotients. So the first line is a recap of what we said before. And then we'll need this number called the A number of an abelian variety. For any x of any dimension, the A number is the dimension of the Homs of alpha p into x, where alpha p is, like before, which I didn't say, the kernel of Frobenius on the additive group. And if we have a PFTQ, Y, such a chain, then we say its A number is the A number of Y0. Okay, so here are some useful facts about the A number, all due to Oort and Lee. Well, for a threefold, we have that its A number is either 1 or 2 or 3. And it's 3 if and only if X is super special, so that it's isomorphic to a product of supersingular elliptic curves. Okay, if a PFTQ is in T in this section, then the A number is 3, so the maximum it can be. Further, if we have a point on C on the Fermat curve, then this is a point over fp squared if and only if the A number of the corresponding PFTQ is greater than or equal to 2, so for anything above that T. And so finally, if we have a Y in P mu, a PFTQ, then this has A number 1 if and only if Y is not in T and the pi of Y is not a point over fp squared on C. Okay, so what this is telling us is that the A number of X tells you sort of where we are in this space, and this will in turn give you some restrictions on what T and U can be. All right, now the next idea is to use these FPTQs to construct what are called minimal isogenies. So any supersingular abelian variety admits a minimal isogeny, which is this map phi here, from Y to X, where Y is super special. And then the idea is that because in an FPTQ, a chain like that, we saw that Y2 is in fact super special. So we can construct our minimal isogenies from the corresponding PFTQs. This will again depend on the A number. So this is what we get. If you start with a supersingular variety X, which has A number 3, then it is super special itself. And so the minimal isogeny is just the identity. But if the A number is 2, then you can show that the A number of Y1, this thing in the middle, is 3. And so the minimal isogeny is just the second map, row 1. Whereas if the A number is 1, then the minimal isogeny comes from the full PFTQ. So we need both row 1 and row 2. Okay, well, why are we interested in this? It's because we can use the minimal isogenies to understand the masses that we were interested in. So if you start with a supersingular variety X lambda, and you look at its minimal isogeny, phi from Y to X, then we can compare the mass of X with the mass of Y. So that's through this lemma here. The mass of the supersingular thing is the mass of the super special thing up to a comparison factor. And this comparison factor is an index of one automorphism group of p-divisible groups inside the other. Okay, so that's really great, but it's especially useful because we know all the super special masses. So this is work due to various people, Ekidal, Arashita, Shimoto, Ibukiyama, and Yu. In fact, the super special masses are known in any dimension, but for three-dimensional varieties, they look like this. So if we start with a super special abelian threefold, then its polarization lambda is either principal, in which case lambda of X actually consists of all principally polarized super special threefolds, and its mass is as given. And if the kernel of its polarization is alpha p squared, the other option, then lambda X is again the set of all isomorphism classes of super special threefolds with that kernel of polarization, and its mass is as given as well. Okay, so everything I've said before kind of gives us a strategy of finding mass formulae for all supersingular varieties, because what we do is we start with one, we find its minimal isogeny using these FPTQs, we know the super special mass, and then we only need to find this comparison factor, the index of the automorphism groups. And moreover, from the lemma, the second lemma on this slide, you can see that if the A number of our variety is 3, then we're already done, because then the first point of this lemma tells us the answer. So the remaining cases then are those of A number 2 and A number 1. So we'll do that in that order. So here we have an x lambda, which is a number 2. Then we've seen that its FPTQ is characterized by a pair T and U, where T is a point over Fp squared. And U cannot be over Fp squared, because then in fact the A number would be 3. Okay. So we have this pair T, U here. And we saw that the minimal isogeny just comes from the last bit, so y1 to x. And so that's the index we need to compute of the automorphism groups of x into y1. Okay, well, how do we do this? This is really, the proofs really work with explicit computations on the GDNA modules and their Fp squared skeleta, but I've decided to not put that on these slides. So I'm going to explain it to you without this theory. But what's important to know is that there are these reduction maps that we can define that send the automorphism group of y1 lambda 1, its p-divisible group, into SL2 Fp squared, surjective. And then it sends the automorphism group of x into SL2 Fp squared, intersected with end U. So this is some set of endomorphisms of our parameter U. So it's all the 2 by 2 matrices over Fp squared, such that G times U is again a K multiple of U. And we can work out explicitly what that is, depending on the degree of U over Fp squared. So I already announced that the mass we'd be finding would depend on the values of T and U, and this is where you see that sort of happening. So how things depend on T and U. Okay. So here's the setup repeated again. And now the index that we need to compute of these automorphism groups is just the index of the reductions of these automorphism groups, which is much easier to compute because we explicitly know what these things look like. So again, we find this index depending on the value of U. And then we're basically done because we know the super special mass, we know the comparison factor. So if we put that all together, then we get the following theorem. So if x is as above, so it corresponds to something with a number 2, then its mass is one of two things, depending on U. Okay, I should also mention that this result for a number 2 is really modeled on a mass formula for 2-dimensional varieties, which was previously worked out by U and U. But now, when we move on to a number 1, things become quite a bit more complicated. So I'll try to just sketch the argument for you in the remaining time. So here, now we start with a threefold that has a number 1. So its FPTQ is again characterized by a pair TU. And now we know that T is not defined over Fp squared. So it's in the C naught of K notation. And since now the minimal isogeny was given by the full flag type quotient, the index that we need to compute is that of x inside y2. So the first one. Okay. So let's start with that. If we have dp be the division quaternion algebra over qp with maximal order ODP, then we can also see this as qp squared adjoint pi. So qp squared is the field of fractions of the width vectors over fp squared. And pi is an element that satisfies pi squared equals minus p. Now this division algebra has a canonical involution, that's star. And then we can show that G2, the automorphism group for Y2, is a matrix group, so of unitary matrices over ODP, 3 by 3. Or, well, call them unitary. So A star A is the identity. And then G, the automorphism group for X, are just the elements inside this G2 that send the p-divisible group of X to itself. Okay, next we want to do sort of the same trick as in the a number 2 case by using a reduction map. So here we're reducing modulo P. Again, it's not quite what happens, but there are these maps, reduction maps, that give us two new groups, G2 bar and G bar, that we can also describe explicitly. So G2 bar is again some matrix group, and they're matrices A plus B pi, where A satisfies some unitary condition and this AB satisfies some symmetric condition. So this in particular tells us what the cardinality of this group is, because we can find it from the cardinalities of the unitary matrices and the symmetric matrices. And this time we show that G bar are all the elements of G2 bar that send the corresponding reduction of the P divisible group into itself. Okay, so since these reduction maps are surjective, we show that the index that we need to compute, which is the index of G and G2, is really the same as the index of the reduced groups, so of G bar into G2 bar. And we already have quite a good handle on G2 bar, so then it remains to study G bar a bit more closely. And we find the following thing. So it's isomorphic again to some matrices. So we see an A, 0, SA, and AP, where A is a unitary matrix that sends T, so this point on the Fermat curve, if you write that in projective coordinates, like T1, T2, T3, to a multiple of itself by some alpha, say. And AP is the matrix where all of the entries are raised to the power P. And S is again some symmetric matrix that satisfies this condition that its image under a map psi T is prescribed and depends on U. So we see that we have both a T and a U in this definition here. And psi of T, didn't want to write down the full definition, but it's a homomorphism from the symmetric matrices into K that depends on T. Okay, now the images under these maps, psi T, if you let T run over the points of the Fermat curve, those define a divisor D inside C0 cross P1, which is a trivialization of our P mu. And for each T, for each point on the Fermat curve, we'll define dt to be the dimension of this image of psi T, and d sub T to be the intersection of D with the fiber above T, which is a P1. So then U is in this dt by definition of the map psi T if and only if UT U1 inverse is in the image. Okay, why is this useful? Because then we know exactly how to compute the cardinality of G, because this clearly depends on this map, mysterious map psi, its image and its kernel. And so we see that depending on whether U is in this divisor or not, and depending on the degree of T, we get exact formulae for the cardinality of G bar. And then again, we are done because we know the super special mass that we need. We know the comparison factor, which is this index of G bar and G2 bar, since we have such an explicit handle on both of these things. So this is the theorem that we then obtain, that if you have an X with a number 1, then its mass is one of three things depending on where U lives and depending on where T lives. Okay. So now we're happy because we know for each super singular abelian threefold what its mass is. But just to end, there's one more question you can ask if there's something else that we can use these computations for. So that will be my last slide. The answer is yes, we can use it to study Oort's conjecture. So this conjecture says the following thing, that every generic G-dimensional principally polarized supersingular abelian variety, n over K of characteristic P, has automorphism group plus minus 1, so as small as it can be. And this is interesting because it's known for ordinary varieties, but it's not clear for supersingular ones. We do know that it's in general false because there are counterexamples in characteristic 2 for dimension 2 and 3 due to Ibukiyama and Oort. But in this case, we can say a lot more, namely that when the dimension is 3, then Oort's conjecture holds precisely when P is not equal to 2. So just quickly, how do you show this? A generic threefold in our case has a number 1, and its PFTQ is characterized by this pair T, U, where T is not defined over FP squared, and where U is not in this divisor that we find. So then our computations, which tell us a lot about the automorphism groups, we can actually go a bit further and show precisely that these automorphism groups are C2 cubed when P is 2, so too big, and they're C2 when P is not equal to 2. So this shows that Oort's conjecture holds in this case. And I'll end here. Thank you very much for your attention.
Thank you for that wonderful talk, Valentijn. Let's clap either audibly or if you can't clap audibly into chat. Great, and we do have time for a couple questions for Valentijn. So I think there were a few questions in chat that were answered by other attendees, but it would be great to type your questions into chat or raise your hand or type them into the Q&A now if you have any. In the meantime, Valentijn, I actually have a quick question. So often when you have a math formula like this, you get a nicer formula when you sum over some set of things you're counting. Like maybe so I was wondering if you get something nice if you sum over all the things defined over FP cubed or FP to the n or something like that, or if you've thought about that at all.
I see, we haven't in fact, but it's an interesting point. We should try that. No, we haven't done that in this case.
Great. Are there any other questions for Valentijn? So there is a question, looks like. Oh, no, I don't think so. All right, so let's wait 10 more seconds, and if there aren't any other questions, let's all thank Valentijn again.